Hello, in this video, we're going to look at graphing polar equations. And when we graph polar equations, it's going to be the same process as graphing Cartesian, where we're going to plot some points and see a general sketch of the graph. But beyond sketching points, there's also symmetry in polar equations that we can look for to make the process shorter. And this symmetry is reminiscent of symmetry we had in Cartesian, where in Cartesian, a graph or function was known as being even if f of negative x equaled f of x. Functions that were even were things like f of x equals x squared, a basic quadratic centered at the origin, or f of x equals cosine of x. Those were examples of an even function. They have a symmetry about the y-axis. What happens on the left-hand side of that y-axis is the same as what happens on the right-hand side of that y-axis. So a mirror is put down the middle. And then for Cartesian, we also had functions known as odd, which is if we take that negative input, we get negative f of x. Example is the graph f of x equals x cubed. Or f of x equals sine. And f of x equals tangent of x. Those were many of our odd examples, and odd reflected around the origin. Symmetry in polar equations works very similarly in that we have symmetry about the x-axis or the polar axis if r theta is on the graph whenever r negative theta is. This is going to look like taking a function r comma theta and plugging a negative in for theta. And if we get the same thing back, this will have symmetry across the x-axis. An example would be the graph r equals cosine theta. Because if I plug in a negative theta, we know because cosine is even in the Cartesian sense, it's going to have symmetry across the x-axis in polar. What this will look like is whenever r theta is on the graph, r negative theta is also on the graph. So there is a reflection over that x-axis. Symmetry about the y-axis is going to look like whenever r comma pi minus theta or negative r negative theta is on the graph, so is r theta. We can check for this by either plugging in pi minus theta and seeing if that's the same as r theta, or we can check for this by saying is negative r theta the same as r comma negative theta. If those two things come out to be the same, then there will be symmetry about the y-axis. How this looks is that if I have that point r theta, then I'd also have the point r pi minus theta. On the graph. Not the same r's in this picture, but it's a symmetry over the y-axis. And an example, something that has symmetry over the y-axis would be r equals sine theta. And then symmetry about the origin is if whenever there's r theta is on the graph, then negative r theta is also on the graph. So this would be when r theta and negative r theta are the same. You notice the input doesn't change here, so more often these are going to be functions that are in terms of theta, and we may have something like an r squared, or maybe something with just r, where the negative will cancel away. Or r equals plus or minus the square root of our function of theta. And some basic examples we have already seen would be things like r equals 3, which is a circle centered at the origin, or theta equals pi over 4, which is a line going through the origin. This symmetry looks a lot like the odd symmetry, where if r theta is on the graph, so is negative r theta. So there's a symmetry around that pole, the origin. So using this idea to sketch the graph of the polar curve r equals 2 minus 6 cosine theta. First, we want to check for some symmetry. And checking for symmetry, because we see this cosine here, that's a good sign to check for the symmetry about the x-axis. So we're going to check that if I plug in a negative theta, do I get the regular function back? So r theta equals 2 minus 6 cosine theta. So r of negative theta, we put a negative in for theta. Cosine is an even function. That means that cosine of negative theta is the same as cosine theta. And sure enough, that is the original function we started with. So r of negative theta equals r of theta. This is symmetric about the x-axis, meaning what happens above the x-axis will also happen below the x-axis. What happens below will also happen above. Just reflect whatever we graph about the x-axis. The second thing we want to do now is plot some points. And because we have the symmetry about the x-axis, this means if we plot from 0 to pi, then pi to pi over 2 will just be the reflection over the x-axis. So going to get some thetas and some r values. Gonna pick theta is 0, pi over 3, pi over 2, 2 pi over 3, and pi. Plugging in 0, we'll get 2 minus 6 cosine of 0, or 2 minus 6, which is negative 4. So when theta is 0, our radius is negative 4. Next, we're looking at pi over 3. When we plug in pi over 3, we get 2 minus 6 cosine of pi over 3. And cosine of pi over 3 is 1/2. So 2 minus 6 times 1/2, which is negative 1. So at our angle of pi over 3, instead of a radius of positive 1, we have a radius of negative 1. When we have pi over 2, we'll have 2 minus 6 cosine of pi over 2, which is cosine of pi over 2 is 0. 6 times 0 is 0. 2 minus 0 is 2. So at our angle of pi over 2, we have a radius of 2. At 2 pi over 3, we'll have 2 minus 6 cosine of 2 pi over 3, which is 2 minus 6 times negative 1/2, which is 5. So at an angle of 2 pi over 3, we'll have a radius 1, 2, 3, 4, 5. So we'll have that point there. And at a radius or angle of pi, we'll have 2 minus 6 cosine of pi, and cosine of pi is negative 1. So we get 8. 1, 2, 3, 4, 5, 6, 7, 8. How we connect these points is, remember, what is increasing is an angle. So we're going to follow an increasing angle around to get, I'm going to zoom in on our graph. As we follow these points we plotted around, we followed in, and it's tracing like we have a circle shape, but connecting those points. So it's a curved connection. And there is half of the graph. Remember, we have symmetry about the x-axis, meaning everything that happened below the x-axis happens above the x-axis, and everything that happened above the x-axis happens below the x-axis. So we get the graph that looks like this looping shape. This bottom part actually probably comes out a bit farther, but in general, we have that symmetric shape. So we can graph polar functions by plotting points and using symmetry. And in the next videos, we will look at how we can now do calculus. Like, can I find the area inside this curve using ideas from calculus?